to record last lecture, which is the Tuesday's lecture. So what I will do is I will again record maybe today in the afternoon. I will again record the video and then I will post it. So maybe it will take time to appear on the Blackboard. Okay, so now let's quickly start. So as you can see, in the last class, we were focusing on the electromagnetic waves. So we were focusing on our electromagnetic waves where, we continued with our the simplest form of an electromagnetic wave, which is E0 cosine omega t minus beta z. And then we did, some, say, simplifications, and we got some, say, terms that defines the electromagnetic wave, or the electric field and the magnetic field, the coupled electric field and the magnetic field. First is the phase velocity, and we found that the phase velocity will be smaller in the material for the electromagnetic wave compared to the free space. Then we looked at the wavelength, we looked at the phase constant, which is very important. And then we looked at the time period and the angular frequency. And I explained it to you how the angular frequency and time, how they are related. This is in time. And now in space, similarly, the wavelength and the phase constants are related. Then we took the example where we tried to find, by looking at the expression of the electric field, we found what is the amplitude, frequency, the phase constant of the electromagnetic wave. And then we also looked at the associated magnetic field. So associated magnetic field, as I told you, now these electric field and magnetic field are coupled, so they exist together. So if this electric field exists, which we got it from the wave equation, what will be its associated magnetic field? And as I told you, we can either solve the Maxwell's equation again, get the wave equation and find the answer, or we can directly use this Maxwell's equation because I know the electric field. Then from the electric field, what is the resulting magnetic field we can find? And we saw that this is the expression. So we found that if my electric field is in the x direction, which is ax E0 cosine omega t minus beta z, then the resulting or the associated magnetic field is in the y direction. So it is this one, where it is here. It is hy beta over mu omega E0 cosine omega t minus beta z. So it will be in the y direction. And what will be the amplitude of this? The amplitude of the electromagnetic field will be this one. And again, its phase constant will be the same, which will be traveling with the same frequency. And this amplitude, we put it under the umbrella of a term called as this bracket term, we call it as an intrinsic impedance, which is root of mu over epsilon. And therefore, now we rewrote the magnetic field as H as, which is HY-AY as 1 over eta, which is this one. And this is nothing but my electric field, EY. The electric field EX. See here? So this is my EX. So the magnitude of my electric field EX. So this is your EX. I would not say magnitude, I would say the expression, because now we have the traveling wave. So this is your magnetic field. And this eta is the intrinsic impedance, which is in the ohms. And then I think based on that, we moved forward. And then we derived the expression for the intrinsic impedance in free space, which is 377 ohms. That it is nothing but root of mu naught over epsilon naught. And then we also got eta expression in general, which is eta naught u root of mu r over epsilon. And then we took this example where we are given this information and we need to find the expression of the electric field and the expression of the magnetic field. So, the frequency, the phase velocity, and the electric field vector is in the x direction, and this is the amplitude. And mu r is 1. So based on that, first we wrote the electric field expression. So how did we write the electric field expression? It is in the positive z direction. So therefore my amplitude is E0 cosine omega t minus beta z, positive direction. And the field vector is in the x direction. So therefore this is in the x direction. This is my electric field. Now we need to find the unknown terms here. So amplitude is given, which is 10 volts. So this is AX is 10 cosine. Now omega, frequency or angular frequency. The frequency is given to me. So I can find the angular frequency, which will be 2 pi times 100 mega, which is 10 to the power of 8 t minus beta c. Now we need to find the phase constant beta. So beta, there are so many expressions, but which one to use? So beta is 2 pi over lambda also, but we don't have the lambda here, right? But we have the phase velocity and we have the frequency or the angular frequency. So therefore we will use beta as omega over u, and we got 2 times 10 to the power of 8 radians per meter. And therefore, sorry, not 2 pi times 10 to the power 8. So just a second. So it is 2 pi times 10 to the power of 8 by 2 times 10 to the power of 8. So which is pi radians per meter. And therefore, this is my electric volts per meter. And how can you get now its associated magnetic field? The associated magnetic field can easily be obtained by the following way. So we know the associated magnetic field is Hy. So see here, it is Hy. So it will be, will be the associated magnetic field. Hy, it will be in the Ay direction, and it is nothing but Ex over eta. So therefore we are finding first eta. So eta is eta naught root of mu r over epsilon r, which is equal to 377 times 1 over root of epsilon r. So here, this is crucial, guys, because here nowhere it is mentioned that our electromagnetic wave is traveling in free space. Anywhere it is mentioned? No. See, nowhere it is mentioned. It is only saying the medium, and it is talking about only, it's a non-magnetic medium. Mu r is 1. So it's a non-magnetic medium. But when you have a non-magnetic medium, it is not necessary that it is a free space. So therefore, you cannot say that eta is simply 377 ohms. So therefore, you have to put mu r as 1, and you need to find epsilon r. So how do you find epsilon r? In this way, because we know our phase velocity, right? And the phase velocity is nothing but c over root of mu r epsilon r. And here everything is known to us except the mu r. So except the epsilon r. So therefore, your root of epsilon r is 3 over 2. And this root of epsilon r, if you substitute here, then you will get eta. So eta is 251.33 ohms. And therefore, my associated magnetic field is Ay times Ex. This is same as Ex over eta, which is 251.33 ohms. So this is 10 volts divided by 251.33 ohms. So it is 0.04 cosine 2 pi 10 to the power of 80 minus pi z amperes per meter. So this is your electric field, and this is the associated magnetic field. Okay, this is the associated magnetic field. And we also spent in the last class looking at the directions. If you see here, you know, our both the magnetic field and electric field, they are both, see, this is your electric field, sorry, this is your magnetic field, and the associated electric field was E bar is equal to AX 10 cosine 2 pi 10 to the power of 8t minus pi z volts per meter. Now let's compare these two. And if we compare these two, what are the important conclusions that we are going to get? First, maybe Mr. Ahmad Al-Ghamdi, can you tell me what is the direction of our magnetic field and what is the direction of our electric field?
Yes, direction is to the positive y.
Positive y. So the first conclusion is, if your electric field is traveling in the positive z direction, then the associated magnetic field also travels in the positive z direction. That means they travel together and in the same direction. Okay. And now, if we look at the direction, which is z, and look at the vector of h, and look at the vector of E, what do we conclude? We conclude that your direction of propagation is always perpendicular to your field vectors. See, Ey and Ez. Or I would say that E bar cross H bar will give me the direction of propagation. So here AX cross AY. So what is AX cross AY? AX cross AY is AZ. And this is my direction of propagation. Because if this becomes my direction of propagation, then your electric field and magnetic field will be perpendicular to each other. See, these two are perpendicular to each other and also perpendicular to the direction of propagation. Okay, so this is a very important, say conclusion. Besides this, yes, both are moving in the same positive z direction, but they will be perpendicular to each other. So the electric field and magnetic field will be perpendicular to each other. That is the component of electric field and its associated component of magnetic field can be perpendicular to each other. So here EX is perpendicular to HY. And both of them are traveling in the z direction. Okay, so this is a very important conclusion. So you can use the idea of E cross H to identify the direction of your electromagnetic wave. You can find the direction of the electromagnetic wave. So if you see here, you have a simple example. So you have an electromagnetic wave E, which is given to you. So let me make it a little bit small so that I can have the problem. Yes. So the problem is saying that you have an electromagnetic wave, and this is the electromagnetic wave. Its electric field is AX. So it has a vector along, so it has a component along AX direction. It is 5 cos 10 to the power of 90 minus 5 by volts per meter. We need to find the direction of propagation. Muhammad Al-Hazmi, can you tell me what is the direction of propagation here? Look at the argument of the cosine. Yes. Now, can you tell me, Mr. Muhammad Al-Hazmi, what is the direction of propagation here? Muhammad Al-Hazmi, you're not there? Okay, Muhammad Al-Humaydan, are you there?
Yes, yes. It will be
Yeah,
at the positive Z.
No. See here, first it is negative sign, right? That means it is moving in the positive direction. Which direction? See,
Yes.
see the direction here.
Yeah, positive Y.
Positive Y. So it is positive Y direction. So it is a positive Y direction. Okay, this is done. Next, the phase velocity of the wave. So what will be the phase velocity of the wave? U is omega over beta, and omega is what? 10 to the power of 9. So it is 10 to the power of 9 over beta is what? 5. So it is 2 times 10 to the power of 8 meters per second. Now, third, if the intrinsic impedance of the medium is 100 ohms, then find the associated magnetic field. So how do we find the associated magnetic field? So now if you see here, now you need to say follow what we just now talked about. That is, we know that E cross H is direction of propagation, right? So now I need the component of H. So how do you find the component of H? Whether Hx will be the associated field of this Y, whether Hy will be there, where Hz will be there, and what will be its direction. Will it be a positive or the negative? So that you can find from this expression. So E is Ax. So Ax cross, we need to find this one. Leave it. Direction. So what is the direction here? Just now we have seen it's a positive Y direction, right? Positive Y. So it is pointing in AY direction. Now, can you find what should be this one? According
Positive
to our
AZ.
Negative AZ.
So it is negative AZ, right? Because AX cross AZ is negative AY, but we want positive AY, it should be negative AZ. That's it. So therefore, the component of H must be a Z component. And in order to follow this rule, it should be negative. So that's why it is negative. So it is minus AZ. This came from here. Then you know it very well. So once you get this, can you just say, or can you just write that EX over, now we know this is HZ. HZ is nothing but your eta. EX over HZ is nothing but eta. In the previous case, it was EX and HY, because previous case, the electric field was different and the direction of propagation was different. But here, it is EX over HZ over is eta. Then sometimes what people do is this negative, rather than showing this negative in, using this one, they, try to show this negative here. So in this case, we will pick the minus sign. Why? Because it is coming here. So therefore we pick a minus sign. But when we pick a minus sign here, then you should not include the minus sign. Okay. So this just depends on you, but you have to consider minus sign in any one case. Either here or here. That means either in the AZ, either with the unit vector AZ or with eta, not 1. So therefore, if you see here, this minus, you can think that this minus is with coming from this 100, which is your eta, because eta is given to you. See, it is 100 ohms, eta. So this one, or it is from this one. You can think from any point of view, it's fine, but not from both, because if you do it from both, again, they will minus and minus will cancel out, which is wrong. And therefore, your electric field, associated electric field is this. So it is in the minus AZ direction. Okay, so this is how you can find an associated field component or an associated field when one field is given to you by using this very important concept that E cross H will point to the direction of propagation. Okay, so here you have another example. We will just look at the direction of propagation. So what is that another example? See here, this is my electric field. So maybe now, Saif Al-Zahrani, can you help me? So what is
Yes, doctor.
propagation here?
Minus AY.
So minus y is the direction of propagation. And what is my electric field vector? AZ, right? So EX or E cross H must be equal to minus AY. So what should be inside this box?
AZ.
Is it, doctor? Not
AZ,
Oh,
doctor,
sorry.
right?
Yeah. Sorry. This is A. This is AZ. Yeah. So AZ cross box is minus AY. So it should be minus AX. Because AZ cross AX is AY, but we want minus AY, so it is minus AX. Yes, we got this. Once we have this, so you already have this. So therefore, it will be what? Just the electric field, the EZ, which is, this is small e, this is the EZ over eta. Eta is 376. Okay. So in conclusion or in summary, these are the important points. The first point is the electric and magnetic field E and H, they propagate in the same direction. We have also seen that excuse me. We have also seen that they travel with the same velocity. See, they are traveling with the same velocity. That means they have the same omega and also they have same phase constant. That's why they are together and they are perpendicular to each other. See, they are perpendicular to each other and also to the direction of propagation. And the last thing is your intrinsic impedance is nothing but root of mu over epsilon, which can also be taken as the magnitude of E over the magnitude of H. This is the magnitude of E divided by the magnitude of H. So if you divide this by this, you will get nothing but the intrinsic impedance. Okay, so these are the conclusions. Now, this is another example. Now, this example, guys, I'm leaving it to you. So you can look at this example at home. Okay, so now let's go to our next lecture. So in the next lecture, what we are doing here, we are just looking at how the electromagnetic spectrum looks like, because we have seen now your electromagnetic field. In your electromagnetic field can have, you know, different frequencies, right? So therefore, now what we are doing is, this is the categorizing of our electromagnetic fields based on the frequencies. And all these are electromagnetic fields. They are all electromagnetic fields. They are all electromagnetic waves. But we are just categorizing according to the frequencies and their common names, and there are some of the applications. So especially if you go here, very small frequencies, 500 to 1 megahertz, which is mostly used for the AM radio, our radio signals, amplitude modulated radios. Then if you go a little bit higher in megahertz, then you use it for FM, frequency modulated radios. Then if you use these frequencies from 400 to 800 megahertz, these are usually used for our television signals. They are all electromagnetic waves, and they're commonly known as just the radio waves, but this is not a common term because radio waves, all of them are called radio waves, but still people use it. This is very common from 3 to 3000 gigahertz. This is called as a microwave region, a very broad classification. And from here, the smaller ones, 2-3 gigahertz, this is our frequency of our mobile communications. So they are all electromagnetic wave, but this frequency is used for mobile communications. Then as the frequency increases, you have different names. So you have, these is for infrared, IR, mostly used for photography and other applications as well. Then you have visible light, 10 to the power of 5 to 10 to the power of 6 gigahertz, visible light. That means these are the electromagnetic waves which you can see. So if you see the light, so light is nothing but it's an electromagnetic wave, but this is visible to us. Then you have ultraviolet, then you have X-rays, then you have gamma rays, and then you have cosmic rays. So these are all electromagnetic waves based on the frequencies, and they have specific applications. So visible light for human vision, UV for sterilization, X-rays for scanning because X-rays cannot penetrate our bones, and gamma rays sometimes they're used for the cancer therapy, and cosmic rays it is just for research. It will be in the astronomy. Okay, so these are the frequencies. Now, how can you find the wavelengths of this one? We know it. Lambda is C over F. I'm not using U here. Okay, I'm not using U here because these are all assumed. They are, these frequencies and the wavelengths, they are assumed to be for the free space. That's why. So instead of U, I'm directly saying C because U and C will be the same for free space. So you can look at how the wavelengths are. So for example, for an AM radio, it will be around 300 meters. And for visible light, it will be like in micrometer. And this is like, say, picofemtometer, 10 to the power of minus 15. Okay. Now, some of the definitions that we always use, the phase. What do you mean by phase? The phase is nothing but the argument of the sinusoid. That is this one. This is called as the phase of the wave. Now, transverse plane. What do you mean by transverse plane? Because now these will be very commonly used terminologies in our electromagnetics, electromagnetic waves and applications. Transverse plane. That is any plane which is perpendicular to the direction of propagation is called as a transverse plane. So if my direction of propagation is this, then these are all transverse plane. Or in the 3D, if you want, if this is my direction of propagation, then these are all transverse planes. See? So if this is Y, then my transverse plane is my XY plane. If this is Z, then XY is my transverse plane. And therefore, if Z is my direction of propagation, then my electric and magnetic field component, they will reside, they will sit in this XY plane because one will be in the X direction, another one will be in the Y direction. Just now we have seen it. Then you have the definition of a plane wave. So what is a plane wave? In a simple manner, although its definition a little bit, difficult to understand, but if you just visualize it, it becomes much easier. That is, what is a plane wave? If the surface of equiphase of the waves are planes, then they are called plane waves. Example, the phase of the above wave is uniform in the XY direction. That is, the surfaces of equiphases are planes. So to just explain this, if you look at this electric field, okay, and if you see that this is my electric field, and my electric field is going in the Z direction, right? So it is in plus Z direction. So what is a plane wave? A plane wave is nothing but so my electric field is AX and my associated magnetic field will be AY H0 cosine omega t minus beta Z, right? H0 and E0, we know the relationship. Let's not worry about that. So they are in AX and AY, right? So your electric field and your magnetic field. So this is your electric field. This is your magnetic field. So what this plane wave is it is saying that this is your electric field, right? And your electric field is moving in this direction and your magnetic field is moving in this direction. But if you look at their phase, it is saying that it is beta Z. That means it is saying that if in this plane, if you go here, and now assume that this plane is infinite. This plane is infinite everywhere. So anywhere you go on this plane, your electromagnetic wave will have the same phase. It will have the same phase beta. It will have the same phase beta. That is called as the plane wave. That is, its phase will be uniform in the XY plane. So wherever you go, your phase will be the same. Your phase is a constant. So that's why wherever you go, the phase will be the same. That is called as the plane wave. And this example of these expressions that we have here, these are all the examples of the plane waves. And these are the simplest form of our EM wave. So therefore, we are not going and looking at complicated types of electromagnetic waves as of now. We are seeing only very simple ones, plane waves. And yes, they are simple, but yet they are very important. They are very important. Why they are very important? In a couple of classes, you will know why they are important. Okay, then the uniform plane wave. A uniform. What do you mean by uniform? That means it comes to the amplitude now. If your amplitude is a constant, then it's a uniform plane wave. If amplitude is not constant, then it is a non-uniform. See, E0 sine Lx. So therefore, if you move in the XY plane, the amplitude is not the same. Although the phase is the same, but the amplitude is changing. It's a function of now my spatial coordinates. That's why it is called as a non-uniform plane. So uniform and non-uniform plane. Now, we have some important definitions here because these are the definitions we are going to use in our next courses. The first definition is TEM. is called as transverse electromagnetic wave. Transverse electromagnetic wave. And we use this word when, see here, when my electric field lies in the transverse plane and my magnetic field also lies in the transverse plane. That is, both electric and magnetic field, both lies in the transverse plane. Then it is called as the TEM. So this is an example where this is my direction of propagation. And if you see here, my electric field and my magnetic field, my electric field is pointing in the X direction and my magnetic field is pointing in the Y direction. So they are in the XY plane. So in the 3D, they are in the XY plane, and this is my direction of propagation. They are in the XY plane. So one is in this direction, another is in this direction. Sorry, Y, in this direction. So, and also they don't have any component here. So my electric field and magnetic field are totally in the XY plane. They are totally in the XY plane. That means my electric field, suppose if it has an X component, and the magnetic field, if it has a Y component, then if you see here, my electric field and magnetic field, they are all completely inside my transverse plane. That kind of electromagnetic wave is called as transverse electromagnetic wave. And this is the kind of electromagnetic wave that will travel in our free space, in our air, free space. This is the one. So it will only have the electric field components in the transverse plane. They cannot have the electric field components in the Z direction, which is the direction of propagation. Because if they have it, then they are classified as different type. If they don't have it, then they are classified as transverse electromagnetic. And we will go and read a little bit more about this transverse electromagnetic. And next is the TE, which is called as transverse electric mode or transverse electric wave. It is called as transverse electric wave. So here the condition is E must be completely inside the transverse plane. H need not be, because H will have a component in the direction of propagation. That means if you see here, this is my direction of propagation, right? Now this is my electric field, which is completely in the X direction, but my magnetic field is at an angle. So if you decompose it, that means my magnetic field has a Hz component and it has a H, how should I put it? Okay, let me draw it and show it to you. I think probably that would be the better in a 3D plane. So what we are seeing is, if this is the plane, then this is my direction of propagation Z. My electric field is here. Okay, but my magnetic field is not in this plane. My magnetic field is something like this. Then if you decompose it, then you will get one component here, which is Hy, and another component here, which is Hc. So this is possible if this is your magnetic field. And this is possible. Why it is possible? Yeah, it cannot be possible in free space where you have unbounded medium. It cannot be possible, but it can be possible in the bounded medium. This is in unbounded medium. And this is bounded medium. Bounded medium, can anybody give me an example of a bounded medium? Yes, Mr. Abdullah Radwan, can you tell me, can you give me a simple example of a bounded medium? That means we are forcing our electromagnetic wave to travel in a bounded medium. That means
Yes.
you are restricting it to go in the transverse direction. You are forcing it not to go or not to move around much in the transverse direction.
Maybe square or medium. Bounded, like a
Say-
plane, but bounded.
Say it again, please.
Like a plane, but it's bounded.
Yeah,
between
it's
X,
bounded.
like-
So,
Yes.
so an example. Okay, I can help you. An example.
Like a wire.
Exactly. It's like a wire, but for electromagnetic waves and for waves which are required for antenna propagation, we don't let's not take an example of a wire, but we take an example of what is called as a waveguide or microstrip line. These are all allowing the waveguide electromagnetic waves to travel, but they are bounded. They are bounding the electromagnetic waves. Means the electromagnetic waves cannot move, cannot go out from here, cannot go out from here, cannot go out from up and down. It should only propagate along this direction, which is the direction of propagation. Direction of propagation. Wire can also be an example. Now, wire is not a good word, but coaxial cable. Coaxial cable is also a very good example. It can go, but since coaxial cable is used for low frequencies, that's why I'm not that much, I don't prefer to give this as an example, but these, because here it is your TE and TM modes that will come into picture. So your TE mode will be available inside this. Because of the bounded medium, this will happen. And this will happen from the boundary conditions. Because, obviously, when it comes to you should think that why you have such kind of electromagnetic wave, why you have, electric field only in this plane, and magnetic field has this and this component. How it is possible, right? How it is possible. And here it's not the case, because in the bounded medium, it comes with the boundary conditions. Remember the boundary conditions of electric field and magnetic field, that will come into picture. That's why those boundary conditions will enforce to have the electric and magnetic field in this manner. And that's why the name transverse electric field or transverse electric modes came. Then the last one is the transverse magnetic mode, where it's the other way around. That means you have the magnetic field completely in the transverse plane, but electric field not necessary. So in this case, the electric field can have a Z component and it can have an X component. That is called as transverse magnetic mode. Then the last one is called as hybrid modes. So in transverse magnetic mode, E doesn't completely reside in the transverse plane. So therefore it can have a component, electric field can have a component in the direction of propagation, that is transverse magnetic mode. Then in the hybrid mode, both electric and magnetic field does not lie entirely in the transverse plane. That means they can have a component in the, both of them can have a component in the direction of propagation. Both can. And this is also possible. And this is possible again for specific type of wave guiding structures. You can have hybrid modes. A simple example of this hybrid modes is your optical fiber. Okay, because optical fiber, it guides light, but it can have this kind of hybrid modes. So it's completely depends on the waveguide. Okay, but in our case, we will only be concerned for, as of now, is the transverse electromagnetic wave. And if you see here, this is how the transverse electromagnetic wave looks like. I will just stop here. And, you know, till now we have been using the expression of phase velocities omega over beta, but this is how you can get. So this is the transverse electromagnetic wave. So this is the electric field. And this is the magnetic field, which is traveling in this way. I will show the animation in the next class, or maybe in I'm making a video in that I can show you. So the phase velocity is nothing but the velocity of the equiphase plane, that is this plane which is traveling. And this will be calculated from the argument, because your argument is constant. So omega t minus beta z, the phase is a constant. So it is a constant. And from here, if you find the derivative, then you will get dz over dt, which is nothing but the phase velocity as omega over beta. Okay. So I think we will stop here. And in the next class, we will take phasors, and then we will go to our next part, which is the lossy electromagnetic waves. Okay. So